Hello, this is Mr. Craig, and I want to talk about examples part 2 for day 102. And even though the heading here says first order reactions and half-life, primarily this discussion will go over second order reactions where there's one reactant. Again, what we talked about on day 100 is a second order reactant. This equation, which is on your equation sheet, again it's located on the front side of your equation sheet underneath the Kinetics heading, bottom left hand corner. This is the equation we want to use for a second order reactant where there's only one reactant, so the reaction is a second order. What this is, it's 1 over the concentration of our substance at some point in time minus 1 over the initial concentration is equal to a positive K times T, which again, that K is your constant and T is the temperature. I'm sorry, temperature is time. So the T is the time here. If we wanted to determine whether the reactant was a first order or second order, that's why I have on here, again, just like on the last video, we want to look at the graph. The data will tell us whether or not we're looking at a first order reactant or a second order reactant. Based on the last video, if I took the natural log of our concentration and plotted it versus time, it would yield a negative slope. Recall that the equation had a negative K. However, if I decide to take the natural log of the concentration for a second order reactant versus time, it will yield a slightly curved graph here. And again, that's not a straight line, so that tells me that cannot be a first order reactant. The way we get a that we get a straight line with a second order reactant is by taking the inverse of the concentration versus time. In that case, that will generate a straight line with a positive slope. So when we go back to our equation here, that's why when we look at our equation, it has a positive K, because it has a positive slope when we take the inverse of that concentration. So the equation itself should be able to help you determine what type of graph you should be looking at to determine the order. So again, this graph over here on the left represents a first order reactant, and the graph here on the far right represents a second order reactant. Do recall that if you do have the natural log of the concentration versus time and it yields something that's sloped, you're looking at a second order reactant. But to be honest, I don't ever recall seeing a question like that on the AP exam. We always want to be concerned with the straight line, so whether it's a negative slope or positive slope. And I'll talk about the zero order graph, I believe, on day 103. But if you want to get the sneak preview here, the spoiler alert, it would be a negative slope, but it would just be concentration versus time. You would not have that natural log there. Because again, remember, a zero order reactant doesn't care what the concentration is, the rate remains the same. Alright, for determining half-life, actually this is probably one of the simpler equations to determine the half-life. All I need to do is take the inverse of 0.5 minus 1 over 1, and we'll do an equation like this here very shortly. But again, don't try to memorize an equation like this to help you with a half-life. It's best to plug in the values. And again, that's my own personal opinion. I'm not somebody that likes to go out and memorize things. But it does make it a whole lot easier if you just say, okay, I'm going to make the concentration at this point in time 0.5 and the initial is 1. Trust me, it will save you a lot of anguish and heartache here. So we'll do some calculations with that here in a second. And I think that's all I want to say about this one. So the graphs primarily are the big topic here that we care about on this one. Okay, let's go work some problems out in the next video.